Welcome back. I'm Dr. Ben Britton, and this is section 2 of this Introduction to Electron Backscatter Diffraction. In this section, we're going to look at EBSD and the measurement, or the understanding of how this relates to crystallographic orientations. This is going to have some basic crystallography to enable people to recap and ensure that pertinent features of the diffraction pattern are understood. So how does EBSD work? Well, EBSD works very broadly is effectively we take a sample, we move the electron beam across the sample, and at each individual point as we move the beam across the sample, we grab a characteristic diffraction pattern, a so-called Kikuchi diffraction pattern. We will then interrogate this diffraction pattern to tell us about the perhaps crystal phase and crystal orientation. Once we've done that, we now have some labels for each point within the map, and then we can reconstruct a description of the microstructure from the ensemble of positions of diffraction pattern and the information that we've measured from each pattern. Now, if we consider what happens in the experiment, broadly, if we have a crystal that's rotating, the crystal will generate a diffraction pattern, and here is a rendering of a spherical diffraction pattern. We insert a detector that measures this diffraction pattern, and we effectively capture this diffraction pattern. So if we can measure features in this diffraction pattern, we can relate that back to the geometry of the system and to the input crystallographic orientation and or crystal phase. So how do we do this? Well, we have to consider some basic geometry. So first and foremost, it's a diffraction technique where we're going to use Bragg's law to our advantage. And we recall that Bragg's law says that n lambda, where n is the order of the diffraction, lambda is the wavelength of the electrons, is equal to 2d sine theta. So where d is the plane spacing and theta is the diffraction angle that's present. In our EBSD experiments, what we see is that we shine an electron beam into a crystalline sample. If we have a diffracting plane that's allowed to diffract from our crystal plane, we will effectively have the presence of a band, a characteristic band that has a specific band width. That bandwidth is the 2 theta angle, and the center line of this diffracting plane contains effectively the source point position that's present here, i.e. where the electron hits the sample, and it contains effectively the perpendicular of the plane normal, and that's the trace of that center line that is inscribed on our insert imaging screen. There are specific geometries, therefore, that are important with regards to the source point position that describes effectively the pattern center. So that's effectively the shortest distance between the screen and the sample. The band center is the diffracting plane that effectively is perpendicular to the plane normal and contains the source point position. And the band width effectively is described by this theta, or in fact 2 theta that's inscribed in here. Now, if we rotate our crystal, what will happen is that we can see that effectively our plane normal will rotate, and effectively our band will move across our screen. And that is the fundamental aspect of measuring the crystallographic orientations. If we can work out which plane this is, we can therefore relate the inscription of the diffraction pattern to the orientation of the crystal. Now, in order for us to do this, we have to recall that each band is a direct projection of the crystal lattice plane, and therefore it's useful for us to have a quick recap on how to index crystal planes. There are many textbooks that will describe this far better than I will here, but I just want to make sure you have some basic understanding to move forward. Another important aspect is that symmetry in the crystals is super important, and so we'll discuss that briefly in this component. A book I can strongly recommend is the Introduction or sort of Basics of Crystallography and Diffraction by Christopher Hammond that has a lot of these ideas presented in it. So a basic introduction to crystallography. Well, crystallography is effectively reflecting that we have metals or crystalline materials are made up typically of a lattice of atoms, often arranged with specific packing. If we consider aluminium as an example, we have the face-centered cubic structure that basically has a cube with an atom on each vertex, each corner of the cube, and then there is an atom in the face center. So we can consider effectively the neighborhood of each atom, or effectively also the number of atoms that are presented in that cube. Specifically, the unit cell describes the smallest tessellating object, that is effectively something that can be shifted in space. And in that tessellating object, effectively there is one atom at the corner, or effectively you can consider there are 8 corner sites. There is an eighth of an atom described per tessellating unit cell. There are effectively 6 faces, each of which have half an atom contained within the unit cell. So there are effectively 3 atoms in the unit cell on the faces. So there are 4 atoms per unit cell for the aluminium crystal structure. Now what we want to think about is where will the crystal planes be in this material, and we need to think about therefore some definitions of the crystal lattice itself. So we describe the unit cell in terms of the lattice parameters. Specifically, we have 6 lattice parameters that are of interest. We effectively have the lengths of the 3 sides. We form a right-handed set with A, B, and C. So we have the right-handed set. And effectively, we have the angles, which are alpha, beta, and gamma. Briefly, the alpha angle is the angle that is opposite the A vector. The beta angle is opposite the B vector, and the gamma angle is opposite the C vector. We can describe effectively the length of the unit cell sides. If it's a cubic structure, A equals B equals C. And if it's a cubic structure, the angles are all equal to 90 degrees. This is all described as the smallest repeating object. This is the unit cell. And we can describe the motif of atoms that are present within that unit cell, i.e. with respect to this cube, in the FCC structure, there is an atom at 0, 0, 0, and there are atoms located in each of the faces. So 0, a half, atoms at a half, 0, a half, and the third, I think, is at a half, 0. So that is the 3 face centers, and then there is the fourth, of course, which is on the vertex. Now within this crystal, we have to consider symmetry, and so the cube itself is it's a very symmetric object. There are a series of different symmetries that we are interested in. Effectively, we could consider the rotational symmetries. For instance, the 2-fold rotation, the 3-fold, and the 4-fold rotation that's present. We can also consider mirror symmetries, and we can consider points of inversion. So I ask at this point, can you see different symmetries that are present in the unit cell? I'm going to ask you just to think about that. So how could you take this unit cell? Where could you rotate it? Where could you rotate it by, say, a 4-fold axis? So if you rotate it about that axis, you will get the same object. If you inserted a mirror into this object, how would you get the same object reappearing? If you put a point and you effectively had an inversion, so the opposite point would come back to itself, that is what you would call an inversion. So can you see those different symmetries? Well, if you have a look, we could look, for instance, at the rotation symmetry, so the 2-fold, 3-fold, and 4-fold. So a tetrad, a 4-fold rotation axis, for instance, lies across the center of the cube. So I can take this cube and I can rotate it by effectively 90 degrees about this 4-fold axis, and I get the same crystal repeating back. And this can be done 4 times, i.e. it's a 4-fold rotation. The 3-fold rotation, this can be found effectively along the diagonal of the cube, what we call the 1, 1, 1 axis. That's this is the triad axis, apologies, there's a typo here. This is the triad that's running along that diagonal. The 2-fold, that dyad axis, that's effectively pointing along from the center of the front here towards the center of the back here. That's that dyad axis. We can see that there are effectively 2 importantly different mirror planes. We have this mirror plane that cuts effectively halfway in the cube, perpendicular to one of the A-type directions. We have this other mirror plane that effectively is running along what we will call in a minute the 1, 1, 1. This mirror plane is running along the 1, 1, 0 type plane, we'll see in a bit, that's effectively cutting along the diagonal here. And we can see if we do a reflection in that crystal, we'll see that this atom reflects to this site over here. Now in the cube, if we formally go through all of these symmetries, there are 24 equivalent cubes that can be found. If you want to think of the thought experiment, the fundamental rotations that are important is that effectively you have 3-fold rotation axis along the diagonal of the cube. We have 2 different mirror planes that will be repeated in here, and then we have a 1 point of inversion. So broadly it's 3 times 2, which is 6, times 2, which is 12, and then we have the inversion, which gives us 24 of those operators. This will be important, as we'll see a bit later. So if we have the crystal, we've got the symmetry that tells us that there are symmetric features and symmetric presentations of the crystal. The important aspect is that that symmetry will be seen also in the presentation of the crystal lattice directions, as well as the crystal planes themselves. Given that the diffraction is created from crystal planes, that's why I've been careful to introduce this idea of symmetry so far. So let's just look at sort of some symmetrically equivalent planes, or how we can consider those crystal planes in our material. So let's start off and let's consider our alumina crystal. And so our FCC crystal would have effectively our faces, our blue objects here, to be identical in chemical speciation, i.e. what atoms present compared to the vertices. So we can see already that if we have our unit cell with our A direction, B direction, C direction, alpha, beta, gamma, these are all identical, they're at right angles to each other. We can see there are atoms that are effectively at each of the corners. There's a quarter of an atom at each of the corners. There is a half atom in each of the faces, and there's the front face and the back face that's present. And these are the atomic sites, the coordinates of those atoms that are present in the cell. Now, if we consider that this object tessellates in 3D, that means effectively we can sort of span across space for those objects. We can effectively put this unit and we can stick another unit on the edge. We can consider how do we move from one atom site to the next. And we can effectively move along, say, an A-type vector. What we can see hopefully is that due to the symmetry of that 1-1-1 type threefold axis, symmetrically it's equivalent to move in this direction as it is within the same family of vectors as to move along this direction as to move along this direction. And so that's starting to be where the symmetry becomes interesting. So in the symmetry, the sort of bonding that's present along the 1-1-1 direction is equivalent to the bar 1-1-1 direction, and effectively the 1 bar 1, and there should be a 1 over here. This results in a family of equivalent directions, and notice that we have specific bracket conventions. So the single square brackets are individual vectors, and the pointy brackets are the family of vectors. Now, in diffraction, we care about the crystal planes, and so we just have to have some conventions about how we index, or what we call those crystal planes in practice. So to do this, I've drawn effectively just a two-dimensional lattice, a two-dimensional cubic lattice, and I'm going to ask how could we index this yellow plane. Note that this yellow plane is exactly the same as a plane that would be located over here and over here. That's due to the tessellation of the unit cell. So how can I index this plane? Well, what I can do is I can draw the basis vectors. So that is effectively A and B of my fundamental unit cell. I draw the basis vectors such that the origin is not located in the plane itself. And what I can see is that this yellow plane crosses A at 1, and it does not cross B, or specifically it crosses B at infinity. I can then calculate the reciprocal of those crossings, so it crosses A at 1, so the reciprocal of 1 over 1 is 1. The reciprocal of 1 over infinity is 0. And I will round to whole numbers. That's important. We'll see that we tend to describe this in terms of the rational indices of the crystal planes. So we'll effectively multiply up to give you a whole number set. So this is the crystal plane. This is the 1, 0 crystal plane in this two-dimensional lattice. If we take this inclined plane here, we can see it crosses the A at effectively a half, and so therefore the index for the A is 1 over a half, i.e. 2. It crosses the B at 1, and 1 over 1, so therefore it is the 2, 1 plane. We can see this example. We can again choose any point for the origin that does not contain the crystal plane. It crosses A at 1/1, it crosses B at 1/1, and so therefore it is the 1,1 plane in the two-dimensional lattice. We can see that if we effectively take this horizontal plane, it now crosses effectively, well, if we put this plane here, we can see it crosses broadly, it crosses at 1/1 for B, and we can see effectively this is equivalent to the 0,1 plane. So the symmetry, the fourfold symmetry about this origin, says that this yellow plane is parallel to this yellow plane, and effectively that says that these two belong to the same family, the 1,0 family of crystal planes. Do note again that this is round parentheses, and this is the pointy brackets that are present, the round pointy brackets for effectively the plane and the family of planes. When we describe crystal planes, we'll often describe the minus sign, if we need it, as the bar 1 plane. Do note that effectively this is related to the index of the plane is related to the plane normal of how this folds. And effectively we can see that if we put this origin, if we put the origin, and if you just bear with me, if we put the origin, we could put the origin effectively above, or we could put it below. It's the same plane. This would cross B at 1/-1. This would cross B at 1/-1. This would cross B at 1/1. And so these two are identical crystal planes in this example. You can work this out for 3 dimensions. It follows exactly the same process, but effectively we can see the families of planes that are present. So this is the 100 type. We can see this is the 110 type that's present. So there are 3 100 types. There are 6 110 types, and there are effectively 12 111 types, I think, in this case. No, I'm wrong. There are 3 110s, there are 6 110s, and then there are effectively 3 110 types. Apologies. 4 110 types in this case. Apologies, I can't count today. And then there are, you can see this sort of follows the different planes that are present. I put these in completeness. If you're unfamiliar with this, please have a look at Hammond's book. This is really important for later on. Now, one of the things we're going to have to do, and it's important for us just to remember, is we're going to have to plot something like effectively a 3-dimensional vector in our 2-dimensional space. One of the methods we can do this is related to what we call the stereogram, and the stereogram has a procedure to plot it. We'll do one example on the next slide. But effectively, if we want to plot this green vector, the thought experiment I have is that effectively I'm starting at the center of planet Earth. I want to describe how to go from the center of Earth to London. And so to do that, I'm going to travel along the green vector. To draw this on the stereographic projection, I then zoom to the South Pole, because effectively London is in the northern hemisphere. I zoom to the South Pole, and the plot on the stereographic projection is effectively where this yellow vector crosses the equatorial plane, in this case. And the equatorial plane contains my reference coordinate system. It contains effectively what I would call perhaps the transverse direction and the rolling direction, and there is the normal direction that's perpendicular. So we can see on this stereogram, I have the ND, that's pointing effectively upwards and downwards, so it's the center point. The RD is pointing across and down, so effectively it's over here. The TD is pointing effectively, we go across and then down. And that vector, the green point, is effectively shown as this blue circle that's located over here. Hopefully you can see, and I'll sketch it in a second, if this green vector was steeper, this blue dot would move closer to ND. If this green vector was less steep, it would move closer towards the edge. Similarly, if I rotated this vector around on the small circle, we can see it will move effectively away. But you can see broadly, effectively, the distance from ND tells you about the angle of the inclination. and the angle around the circle effectively tells you about the angle, for instance, towards the TD vector, or the decomposition of that. So this is simply, it's worth practicing, and we'll do one example in a second, but it's important that you follow the recipe, that we pick a direction. We go to the edge of the globe from the center. We then go to the opposite pole. We plot the intersection of that vector with the equatorial plane, and we make sure that, as any good graph or figure, we put the reference axes of our system that's present. So if I just take an example, so my drawn example, so if I want to effectively plot a vector in here, so if I just take a vector and I point it over here, I go from the center over here, I go towards the edge, I then go from the edge and I plot downwards to go to the opposite pole, and the stereographic point is the point effectively where it crosses that equatorial plane. So in my stereogram, it would look like this point is somewhere over here. If I change and move that point further out, so I go for a less steep vector, we can see it will go down. We follow the same recipe. We then plot it further out, and we can see if it's effectively collinear. Sorry, it contains in that same zone, apologies, cozonal. Then we can see it will be pointed out there. So the distance, the angle here, between this point and this point, is describing, it's a relationship and it can be calculated, but it's the angle theta is encoded in that distance. If I effectively moved this vector, so I can take one that's running over here, similar to my example that I started with, so I could put that, effectively it could sit over there. And I could now effectively spin around this circle, the small circle on the top of the sphere, and I could then plot, let's change the color again, I could plot up, so it's obtaining the same angle. It could then go down to the negative pole, plot it there. What will happen effectively is it will sit on this small circle, and that new point would be located there, over there. Now some of you may ask, how do you plot something in the negative hemisphere? So if imagine that you had a vector pointing downwards and you then wanted to go up. Well, what you could do is you could simply change the notation to put effectively a negative as a circle. You could put a key and say that's a positive vector. And you could put a circle to have the negative vector in there. And we'll see that being used a bit later. Again, if you're unfamiliar with this, I would suggest you have a practice, pause the video and have a practice in your own time to check you understand at least how you go from a point, from the vector to a point, and how you do the reverse operation. And so by that, apologies, if I just go to the next slide to give you an idea. So if I then take effectively some point that's present here, how would I find that? So I could draw this in 3D, this point. I would then go from the hemisphere pole back to the center, and so that is the vector that that stereographic point matches to. So please do that, have a little bit of practice, sketch a few goes yourself, and when you're ready you can join me again in lecture 3.